You know that little pill you take for a headache? It can feel like a tiny magic bullet. But have you ever stopped to wonder how it knows where the pain is? Well, today we're going to pull back the curtain on the secret life of painkillers. And I'll tell you right now, it's not magic. It's a fascinating story about your body's own hidden communication network and how we've actually learned to hack it. And that is a great question, right? Because the answer is way cooler than magic. Here's the spoiler. Painkillers don't actually go to the pain. They aren't these tiny little heat-seeking missiles. Instead, they work by interfering with a conversation that's already happening all over your body. To get how that works, we first need to meet the messengers. Okay, so the key players here are a group of chemicals called autocoids. Now, you've definitely heard of hormones, right? Think of those as a national broadcast, sent out through the bloodstream to affect the whole body. Well, autocoids are totally different. They're like hyper-local text messages, sent from one cell only to its next-door neighbors. They're made on the spot for a super specific local job. And when it comes to most painkillers, this entire story really hinges on one specific group of these autocoids. It all starts with a single molecule found in our cell membranes, which suddenly finds itself at a fork in the road, a critical decision point that ends up shaping everything from pain to inflammation and fever. So this might look like a page from a super intense chemistry textbook, but just stick with me because this is the blueprint for pain. Right here in the middle, you can see our cell membranes releasing this fatty acid called arachidonic acid. You can think of this as the raw material. And from this one single starting point, you can see all these arrows branching off to create all sorts of different signals, the very ones that cause pain, fever, and inflammation. The path it takes, that's everything. So let's properly meet our protagonist, arachidonic acid. Whenever a cell gets damaged or stressed out, this molecule is released, and it has to go down one of two pathways, which are controlled by different enzymes. The specific path it chooses dictates the exact kind of ouch message that gets sent out. So if these pathways are like a conversation happening inside our bodies, this is where medicine gets so clever. We can essentially hack the system. By designing drugs that block one path or the other, we can intercept those pain messages before they're even fully sent. And that is the secret behind one of the most common classes of drugs on the entire planet, NSAIDs.
So one of the main pathways is controlled by enzymes called cyclooxygenase, or just COX for short. And there are two main types. I want you to think of COX-1 as the diligent housekeeper. It's always on, 24/7, doing essential daily chores like protecting your stomach lining. COX-2, on the other hand, is the inflammation specialist. It's the emergency crew that only gets called in when there's an injury or things get inflamed.
So, how do non-steroidal anti-inflammatory drugs, or NSAIDs, actually get the job done? Well, it's almost beautiful in its simplicity. They just block these COX enzymes. The drug molecule literally gets in the way, stopping the enzyme from working and shutting down the entire assembly line that produces the molecules causing pain, fever, and inflammation. But here's the thing, not all NSAIDs are created equal. Some, like the ibuprofen and aspirin you probably have at home, are non-selective. They're like a sledgehammer, blocking both the housekeeper and the emergency crew. Others are way more targeted. The preferential and selective COX-2 inhibitors, they try to only block the emergency crew, leaving all those good housekeeping functions alone. And this, right here, is why different painkillers can have such different side effects. Okay, so how does this actually play out with the pills in your medicine cabinet? Let's compare two absolute giants, aspirin and paracetamol. Aspirin is a classic NSAID. It's a potent COX inhibitor all throughout the body. But paracetamol, which you might know as acetaminophen, is still kind of a mystery. It's a pretty weak inhibitor out in the body, which is why it doesn't do a whole lot for inflammation. Its real power seems to be inside the central nervous system, in the brain and spinal cord, where it blocks pain and fever signals right at their source. All right, so blocking these pathways to stop pain, that makes total sense. But here's where the story takes a really fascinating turn. It turns out the molecules they block, which are called prostaglandins, do a lot more than just cause pain. They have some truly surprising and absolutely vital jobs all over the body. Take your blood, for instance. You've got two prostaglandins locked in this constant tug of war. One of them, PGI2, is the relaxer. It widens your blood vessels and makes blood platelets less sticky. Its counterpart, TXA2, is the clotter. It does the exact opposite, constricting vessels and telling platelets to clump together.
Your body is constantly fine-tuning this delicate balance just to keep everything flowing smoothly.
And hey, here's another surprise. Remember our friendly housekeeper enzyme, COX-1? Well, one of its main gigs is producing prostaglandins that create a protective mucus lining in your stomach. And this is exactly why you hear warnings about taking too many non-selective NSAIDs, because you might be accidentally shutting down the housekeeper.
And it doesn't even stop there. In what has to be one of the most profound biological processes, prostaglandins are the absolute star players. They are so critical for preparing the body for childbirth that synthetic versions are actually used in hospitals to induce labor. It's just a stunning example of how these tiny, local messengers can orchestrate one of life's biggest and most complex events.
This slide illustrates their importance even before birth. It's amazing. If you look at this diagram on the left, you'll see a fetus. Prostaglandins are responsible for keeping a special little blood vessel, the ductus arteriosus, propped open. This allows blood to bypass the lungs, which, aren't being used yet. Then, almost immediately after birth, prostaglandin levels plummet and that vessel slams shut. This is precisely why most NSAIDs are a huge no-go late in pregnancy. They could shut that critical gateway way too early.
So think about that. The same family of molecules that helps with childbirth and protects our stomachs is also what we block to stop a simple headache. That's the power of autocoids. But prostaglandins are just one chapter in this story. To see just how diverse these local messengers are, let's look at another famous one, the one that goes completely haywire during an allergic reaction. Everybody, meet histamine. This is the local messenger responsible for all those classic allergy symptoms, the itchiness, the swelling, the redness. When your body encounters an allergen, like pollen, certain cells release a flood of histamine right into the immediate area. And this flood of histamine kicks off a classic chain reaction called the triple response, which you've definitely seen before. First, you get the red reaction. Local blood vessels widen. Second comes the wheal. Those vessels become leaky and fluid seeps out to create that swollen, itchy bump. And third, you get the flare. The redness spreads out to the surrounding area. It's a perfect, visible demonstration of these local text messages in action.
So when you just step back and look at the whole picture, it's pretty clear that these tiny local molecules are the unsung heroes of our biology. I mean, we started with a simple headache, but we've seen how they manage everything from inflammation and blood flow to protecting our organs and even orchestrating the miracle of birth. They're just constantly running the show from behind the scenes.
And that leaves us with this really fascinating question for the future. We've gotten very good at intercepting these messages to manage pain. But as we understand this incredibly precise local communication system better, what other conversations could we join? What other diseases could we treat by targeting just the right message in just the right place at just the right time? The possibilities, they're really exciting to think about.